Today we'll be seeing with the next module, which is module 4, the overvoltage phenomena and insulation coordination in electric power systems. Here I'll be reviewing the natural causes for overvoltages, what exactly is the lightning phenomena, how the lightning takes place. Also we'll be studying here the overvoltage due to switching surges, system faults and other abnormal conditions. What are the principles of insulation coordinations on HV and EHV power systems? So first we'll go to the causes of overvoltages in power system. Right, here we'll be studying with natural causes. Okay. So as we know, lightning phenomena is a peak discharge in which charge accumulated in clouds discharges into a neighboring cloud or the ground. So the electrode separation, that is either cloud to cloud or cloud to ground, is very large here. So almost perhaps 10 kilometer or more, right? The mechanism of charge formation in the clouds and the discharge is quite a complicated and uncertain process, right? But nevertheless, here a lot of information has been collected since last few years, right? And several theories have been put forth for explaining the phenomenon of lightning, right? So we'll one by one see the various phenomenon suggested by various readers and the theorists. Okay. So first one we'll see the charge formation in the clouds. The factors that contribute to the formation or accumulation of charge in the clouds are too many and uncertain, right? But during thunderstorms, positive negative charges become separated, right? Positive and negative charges become separated by heavy air currents with ice crystals in the upper part and rain in the lower parts of the cloud. So this charge separation depends on the height of the clouds, which can range from 200 to 10,000 meters, with their charge centers probably at a distance of about 300 to 2000 meters, right? So the volume of clouds here, the volume of clouds that participate in lightning flashovers are uncertain. Okay, these are uncertain, but the charge inside the cloud may be as high as 1 to 100 centigrade. Okay, so the clouds may have the potentials as high as 10 power 7 to 10 power 8 volts with field gradients ranging from 100 volts per centimeter, right, at the initial discharge point. Okay, so within the cloud, and to as high as 10 kilovolt per centimeter at the initial discharge point. Okay, so the maximum gradient, what we are talking, the maximum gradient reached at the ground level, the maximum gradient reached at the ground level due to a charged cloud may be as high as 300 volts per centimeter, while the fair weather gradients are about 1 volt per centimeter. Okay, so the energies associated, right, with this, with the cloud discharges, it can be as high as 250 kilowatt hour, right, but it is believed that the upper regions of the cloud are usually positively charged. Okay, so if you assume a cloud, okay, it is generally assumed that upper regions of the cloud are positively charged, whereas the lower region and the base, okay, this is your lower region and the base, are predominantly negative charged, okay, except the local regions, okay, near the base, okay, and the head, right. So as I said, here the maximum gradient which is reached is 300 volts per centimeter. Okay, so a probable charge distribution model, okay, that I just showed you is given in the figure, right. What I showed you just now, you have a charge distribution model. Okay, so this is the charge distribution model where the topmost part of the cloud is assumed to be positively charged and the bottom portion is assumed to be negatively charged. If you have ground here, okay, we'll have ground here, so there will be distribution of charges or transmission of charges either from cloud to cloud or from cloud to ground. Okay, so this is my field gradient at the ground. So this is positive, this is negative, this is the total field gradient. Okay, now according to Simpson's theory, okay, according to Simpson's theory, there are three essential regions in the cloud to be considered for charge formation. Okay, so there are three essential regions in the cloud. So as I showed you, you please remember, right, this was the cloud, okay, the upper part was charged with positive, right. So let me say there are three regions, A, B and C. Okay, so according to Simpson's theory, there are three essential regions in the cloud to be considered for charge formation. Okay, so below A region, okay, here let me say this is the rain, okay, this is positive rain region, this is negative rain region, right. So below region A, air currents travel above 800 centimeter per second. Okay, so below region A, what I said, see, below region A, the, just a minute, okay, so you can see here, below region A, air currents travel almost above 800 centimeter per second and no raindrops fall through this. So okay, so below region A, air currents enough to break the falling raindrops. Just a minute. Okay, so falling raindrops causing positive charge spray in the cloud and negative charge in the air. So the spray is blown upwards, okay, spray is blown upwards, but as the velocity of the air reduces, the positively charged water drops recombine with larger drops and fall again. Okay, so therefore, thus the region A eventually becomes predominantly positively charged, while region B above it becomes negatively charged by the air currents. Okay, so as you have to remember the figure, right, I had shown you three regions. One region, okay, where topmost of the cloud is positively charged, bottom is negatively charged, this would be my region A. Then above region A I have region B, above region B I have region C. Okay, just remember this figure. I'll go on explaining what happens or what was the Simpson's theory. Okay, so this is the Simpson's theory for, see, Simpson's theory for region A, right. So thus as I said, in the upper regions in the cloud, the temperature is low. Okay, in the upper regions in the cloud, the temperature is low, almost below freezing point. Okay, almost below freezing point, and only ice crystals exist here. Okay, only ice crystals exist here. The impact of air on these crystals make them negatively charged, thus the distribution of charge within the cloud becomes, okay, as shown in the figure. So in figure what I'll show, I have according to Simpson's theory, right, when I incorporate all this, okay, according to Simpson's theory, the top part is positively charged and the bottom part is negatively charged, right. I have positive rain here, I have negative rains here. Okay, so air currents are flowing like this. This is my region A. So above region A I have region B, above region C I will take my region C. Okay, so there are three regions. So this explanation I have given you for region A. Okay, so in region A, right, the air currents, as I said, below region A, the air currents enough to break the falling raindrops. Okay, are enough to break falling raindrops, and no raindrops falls through. So the speed of the air is of almost 800 centimeter per second. As I said, air velocity is high. Okay, here air velocity is high. The spray is blown upwards. See, I have shown upward direction of the air blow, right. But as the velocity of air decreases, the top of the cloud, right, here the upper regions in the cloud where the temperature is low, only ice crystals are existing. Okay, so the impact of the air on these crystals make them negatively charged, thus distribution of charge within the cloud becomes as I show you, right, as I have shown to you. Okay, right. But recently above Simpson, Reynolds and Mason proposed modification according to which the thunder clouds are developed at the heights of 1 to 2 kilometer above the ground level and may extend up to 12 to, and these thunder clouds may extend up to 12 to 14 kilometers above the ground. Okay, so the air currents controlled by the temperature gradient move upwards carrying moisture and water droplets. The temperature is about 0 degree centigrade at about 4 kilometers from the ground, and it may reach up to minus 50. This has to be minus, so it may reach up to minus 50 degree centigrade at about the height considered to be, say, 12 kilometers. Okay. So the larger number of solid sites or nuclei present, the higher is the temperature. Okay, the temperature can go above minus 40 degree centigrade at which the ice crystals grow. Okay, this is the temperature at which the ice crystals grow. The water droplets in the thunder cloud are blown up by air currents and get supercooled over a range of heights and temperatures. When such freezing occurs, the crystals grow into large masses. Okay, when such freezing occurs, the crystals grow into large masses and due to their weight and gravitational force start moving downwards, right. So thus A thundercloud consists of supercooled water droplets moving upwards and large hailstones which are moving downwards. So when the upward moving supercooled water droplets act on the cooler hailstones, those freezes partially. Okay, there will be the partial freezing of the hailstones. When the process of cooling extends to inside warmer water in the core, it expands, thereby splintering and spraying the frozen ice shell. This I am talking about zone B. Okay, this we are talking about zone B. So, the hailstones that travel downwards, right? The hailstones that travel downwards carry an equivalent negative charge to the lower regions of the cloud, and thus negative charge builds upon the bottom side of the cloud, right? So this is the reason why I had showed you the cloud model, right, according to Simpson's theory, where the bottom of the cloud was negatively charged. Okay, according to Mason. Okay, now here according to Mason, the ice splinters should carry only positive charge, that too in the upwards. Okay, because water being ionic in nature has concentration of H plus and OH minus. Okay, this is H plus, this is H plus and OH minus ions. Thus, an ice slab with upper and lower surfaces at temperatures T and T2, where T is less than T2, okay, T, or let me consider this as T1, okay, let me consider this as T1. T1 is less than T2, there will be higher concentration of ions in the lower region, okay, in the lower region. However, since H minus ions, since H plus ions are much lighter, they diffuse much faster all over the volume, right? Because of this, the lower portion, which is warmer, will have a net negative charge density, and hence the upper portion where we had considered the positive charge, right, that is the cooler region, will have a net positive charge density, right? Hence it must be appreciated here that the outer shells of the frozen water droplets coming into contact with the hailstones will be relatively cooler, and therefore they acquire a net positive charge. Okay, they'll acquire a net positive charge. Okay, net positive charge. So when the shell splinters, the charge carried by them in the upward direction is positive. Okay, it is positive. Now, according to the Reynolds theory, okay, you remember Reynolds and Mason have given the improvement in the theory above Simpson's theory. So according to Reynolds theory, which is based on the experimental results, the hail packets get negatively charged when impinged upon by warmer ice crystals. So when the temperature conditions are reversed, the charging polarity reverses. However, the extent of the charging and consequently the rate of charge generation by Reynolds was found to disagree with the practical observations relating to the thunderclouds. So this type of phenomena also occur in the thunder clouds where the theories do not agree with the practical results. Right? So, in the next video, we'll see the rate of charging of thunder clouds. Thank you.